Bayesian learning. Bayesian reasoning provides a probabilistic approach to inference. It is based on the assumption that the quantities of interest are governed by probability distributions. Why is Bayesian learning important for machine learning? Bayesian learning algorithms that calculate explicit probabilities for hypotheses are really necessary. Like naive Bayes classifier is among the most practical approaches to certain types of learning problems. They provide a useful perspective for understanding many learning algorithms that do not explicitly manipulate probabilities. Now, moving to features of Bayesian learning, each observed training example can incrementally decrease or increase the estimated probability that a hypothesis is correct. Prior knowledge can also be combined with the observed data to determine the final probability of a hypothesis. Bayesian methods can accommodate a hypothesis that make probabilistic predictions. For example, a certain patient has a 93% of chance 93% chance of complete recovery. Then, one practical difficulty in applying Bayesian methods is that they typically require initial knowledge of many probabilities. Also, a second practical difficulty is that a significant computational cost is required to determine the Bayes optimal hypothesis, which is difficult to calculate, and in the general case, it is not easily acquired. So, this is also a second practical difficulty. Then, Bayes' theorem is basically used for determining the best hypothesis from some space H given that observed training data D. Now, one way to specify that what we mean by the best hypothesis is to say that we demand the most probable hypothesis. So, whichever has the most highest probability, that will be our demanded hypothesis. Then, given the data D plus any initial knowledge about the prior probabilities of various hypotheses in H, Bayes' theorem provides a direct method for calculating such probabilities. So, Bayes' theorem provides a direct method for calculating any probabilities whenever a certain data and some prior knowledge is given. Then, for example, there are 100 people in a school and they are classified as male, female, teacher, student, so on. So, what is the conditional probability that a certain member of school is a teacher given that he is a male? So, what is the probability that if we know that a person is male, then he is a teacher? What is the probability of that? So that is easy. We will just you get the probability of male intersection teacher. We will get the probability of male intersection teacher upon the probability of total males. So the number of total males actually. So if we do that, we'll get the probability of probability of teacher given male. So we can see that probability of teacher given male is probability of teacher intersection male upon probability of male. So we can just directly see that it is 0.2. So we come to the notations. P of H is used to denote the initial probability that hypothesis H holds before we have observed the training data. Then P of H is also called the prior probability of H and may reflect any background knowledge we have about the chance that H is a correct hypothesis. If not possible, we can simply assign the same prior probability to each candidate hypothesis. Now, P of D is to denote that what is the probability of the given data. It does not require any prior knowledge or any hypothesis. It is not dependent on the hypothesis. It is just the general probability of the training data D. Now we come to P of D given H. It is the conditional probability. If H is true, what is the probability of D? That is the conditional probability. So P of D given H. Then we come to P of H given D. This is called the posterior probability of H. So we know what is the probability of D if H is the correct hypothesis. Now we need to know what is the probability that H is correct hypothesis given that we have D training data. Now this posterior probability is calculated using the Bayes theorem, which gives us P of H given D is equal to P of D given H into P of H upon P of D. Now the learner considers some set of candidate hypothesis H and is interested in finding the most probable hypothesis H, given that the observed data is D. Now for that we can use Bayes theorem easily. Any such maximally probable hypothesis is called a maximum a posteriori hypothesis, map hypothesis. So we can determine the map hypothesis by using Bayes theorem to calculate the posterior probability of each candidate hypothesis. Now we need to get more details about map. So H map is a map hypothesis provided. H map gives argmax P of H given D. Then H given D is calculated using the Bayes theorem, so we get the probability of H given D here, and then we can just drop the term P of D because it is a constant which is independent of the hypothesis H. So we have just removed the P of D here. In some cases, we will assume that every hypothesis in H is equally probable a priori. So sometimes we can just assume that P of Hi is equal to P of Hj and all the hypotheses have the same probability. Then P of D given H is often called the likelihood of data D given that H hypothesis is correct. Any hypothesis that maximizes P of D given H is called a maximum likelihood hypothesis, HML. So wherever the P of D given H is the maximum, it is called the HML. Now we can come to this example where we have two hypotheses that the patient has particular form of cancer and the patient does not have the cancer. The available data is from the particular laboratory test with two possible outcomes, positive and negative. We have prior knowledge that over the entire population of people, only 0.008 have this disease. And the test returns a correct positive result in only 98% of cases in which the disease is actually present. A correct negative result is only 97% of the cases in which the disease is not present. In other cases, the test returns the opposite result. So from this we can say that if a person has cancer, that probability is 0.008, not having cancer is 0.992. Then a correct positive of cancer is 0.98, wrong false negative of cancer is 0.02. Then again here it comes positive but the person has no cancer, it is 0.03, and it comes negative and the person does not have cancer, it is 0.97. Now suppose we now observe a new patient for whom the lab test returns a positive result. Should we diagnose the patient as having cancer or not? What should be the probability of that? So we can get that probability that we have the positive result and we need to know if the person has cancer or not. So for that we will use the given probabilities here. So we'll just directly take positive given cancer into P of cancer. Since we have already removed this, where is it? And since we have already removed P of D because it was a constant, so we need not to calculate the denominator. So we'll just take P of positive given cancer into P of cancer. So that probability is 0.0078. Then again, since the result is positive and we also need to know what is the probability of the person not having cancer given that result is positive, we will take probability of not cancer given positive. So that will be P of positive given not cancer into P of not cancer. So when we multiply that, we get 0.0298. So from here we can determine that the probability of the person not having cancer is more than the probability of the person having cancer with the positive result. So So the exact posterior probabilities can also be determined by normalizing the above quantities so that they sum to 1. So we can also get something like this, that P of cancer, given that test result is positive, is 0.21, since we have normalized it. And uh, and then P of not having cancer, given that result is positive, we get the that possibility as 0.79. So here also we can see that the person is more likely to not have cancer than to have cancer. The result of Bayesian inference depends strongly on the prior probabilities, which must be available in order to apply the method directly. In this example, the hypotheses are not completely accepted or rejected, but rather become more or less probable as more data is observed. Now we come to our second problem. So suppose we have a football game between two rival teams, team 0 and team 1. Suppose team 0 wins 95% of the time and team 1 wins the remaining matches. Now among the games won by team 0, 30% of them come from playing on team 1's football field. And on the other hand, 75% of the victories for team 1 are obtained while playing at home. If team 1 is to host the next match between two teams, which team will most likely emerge as a winner? So again, we can get direct probabilities of team 0 winning is 0.95, team 1 winning is 0.05. And probability team 1 hosted the match and team 0 won the match is 0.3, whereas the probability that team 1 hosted the match and it won was 0.75. Now, if we want to know if team 1 hosted, which team will if team 1 hosted, the winning team will be team 1 only. So for that, the winning team will be team 0. So our hypothesis 1 tells us that if team 1 hosted, winning team will be team 0. So to check that probability, we will just directly multiply probability of team 0 winning into probability of team 1 field given team 0 won. So yeah, here we get the probability as 0.285. And if we divide 0.285 with 0.317, which is the probability of what which we are actually normalizing it, which we are actually normalizing it. So using this summation of both the probabilities, we are doing the summation of both the probabilities and then we are normalizing it. So our probability is 0.88. And we're checking if hypothesis 2 given team 1 hosted. So our hypothesis 2 is that team 1 actually wins the match. So we are checking our hypothesis probability of our hypothesis 2 being correct given team 1 hosted. So it will be probability of team 1 winning into probability of team 1 field given team 1 has won. And so if we do that, our probability will be somewhat 0.0375, and after normalizing it we'll get 0.12. So again we can tell easily that team 0 wins this match. Now similarly we have a few more problems, like a company buys 70% of its computers from company X and 30% from company Y. Company X produces one faulty computer per 5 computers and company Y produces one faulty computer per 20 computers. A computer is found faulty. What is the probability that it was bought from company X? So to get that, we first get the probabilities. So the probability of a computer from X is 0.7 and the probability of computer from Y is 0.3. Now the probability of X producing faulty computers is 1 by 5, which is 0.2, and the probability of Y producing faulty computer is 1 by 20, which is 0.05. Sorry, 0.05. Now a computer is found faulty. So we have two hypotheses, which so we'll check the first one, that the computer, given that a faulty computer, it is from company X. So we'll again use the Bayes theorem, which is this given probability of hypothesis given data D is equal to P of D given H into P of H. So we'll just directly multiply the probability of X into, yeah, wait, yeah, so we will just directly multiply the probability 0.7 into this probability of X producing the faulty computer, so which is 0.2. So we'll multiply the two and then we'll get the result. And so here we have some formulas, like product rule is here, then sum rule is also here, and Bayes theorem is here, which is the most important one. So we have this Bayes theorem, and then we have theorem of total probability. So this is the theorem of total probability, that P of B is equal to summation of 1 to n P of B given AI into P of AI. Then we come to product rule examples. We will start from here in the next video. Thanks a lot for watching, everyone.